I believe everyone knows. I posted the third lab assignment on the Blackboard. Okay, so I believe you can see the lab assignment document. I shared this document. So the goal of this third lab assignment is to design single cycle processor. So we learned how to design the single cycle processor in chapter 4. And then, as I mentioned, the single cycle processor execute one instruction per cycle. So that means the result of an instruction is updated to the architectural state. And then I mentioned the architectural state is the register file and memory. So data memory, that means. So that means the instruction complete each operation within one clock. So we learned. So and then this lab assignment is to implement this single cycle processor using system Verilog HDL. So HDL means hardware description language. And then we already used this HDL, the lab assignment 1 and 2. And then I believe I know some students struggle to design this Datapath element using the system Verilog. So, but I already posted some tutorials for system Verilog and then how to design, how to implement the test bench, and then very simple design using the Verilog. So please read the document on the Piazza that is posted on the Piazza. Also, for this third lab assignment, I include the completed Datapath element design. So that means in the second lab assignment, you were requested to design instruction memory, register file, ALU, and data memory. And then for this third lab assignment, I already provide the completed design. So it works. It will work well. So do not give up this third lab assignment, even if you fail to complete the second lab assignment, because I provide the completed Datapath element. And then if you fail to complete the second assignment, then please refer to my Datapath element design. And then please figure out what is required for this completed design. Okay. And then for this single cycle processor design, I provide the assembly code. So this is the assembly code, and then this assembly code can be represented as the machine binary code like this. So as you can see, this one line assembly code can be represented this binary code. So it's a machine language. And then this code is stored in the instruction memory. So this instruction is fetched from the instruction memory every cycle. And then what is the address for these instructions? Program counter. So Unity designed also this program counter. Then actually the program counter starts from the PC for this instruction. Okay, and then for the next instruction, it will be pitch +4. So then the new program counter will point the address of the next line. Okay. Then also I also provide the incomplete test bench. And then in the test bench, actually the test bench will generate the report file. And then this report file will read the content of a register file and the part of data memory. And then it will print out the content of this register file and the data memory. So, and then one student already posted a question on the Piazza, on Piazza, and then what's that? So golden file for this report.txt will not be provided for this lab assignment because we will use this golden file to check your student's design is good or bad. So we will not provide the golden report file, but for this third lab assignment, you can check the content of the register file and the data memory when the one instruction complete each operation, the single cycle processor. So for example, so what is the first instruction? It's a load word. So unfortunately, this processor is the 32-bit processor, not 64-bit. But the difference is this loading the width of the register file, and then we will use the load word instead of a load double word. So the first instruction is the load word, and then as you can see, if this load word is executed, this load word access the address 0 for the data memory, right? Because x0 is the 0. And then so actually I also provide the initial data for the data memory. So it will exist in the data memory when you run your design, this single cycle processor design. So this load word read data from the address 0 and then store this content of the address 0 in x4. So for this instruction, you can check the content of the register file x4, and then if the content of the x4 is equivalent to the content of the data memory of address 0, then your design, that means your design works well. So this is how to debug your this single cycle processor design for this third lab assignment. Okay. So this is the implementation. This is a lab assignment. It's an implementation lab assignment, and that is also very important because so you may think that we already know how to design the single cycle processor because we learned how to design in the classes, but you will know perfectly if you implement one using some real code or some real programs. And then it's also true for the other programming. It's a programming course like Python or C++ or C. That means the programming courses. So you can learn how to use some statement or command or syntaxes for Python or C++. It's a programming language, but you cannot say you know how to program the Python or C code before you complete your own design using these high-level languages. And it's the same to this hardware design, right, or the processor architecture. So you may already know how to design the processor architecture, but before you complete the your own design using the hardware description language, then you cannot say, I know how to design this single cycle processor. So that's why I provide this lab assignment using the hardware description language. So it may be it may not be easy for some students because this is some hardware related design, not software. So if you have any issues or questions, please post your questions or issues on Piazza, and then the course TAs or I will also answer the questions. Okay. Any questions for the third lab assignment? In the previous class, we learned about the data forwarding path in the pipeline processor. So I believe students already understand why the data forwarding is required. So if there is no data forwarding path in the pipeline processor, then we need to store the dependent instructions, because so in the pipeline processor, the destination register is stored or written back to the register 5 in write back stage. That is the final stage of pipeline processor. So and then in order to reduce the wasted cycle by these data dependencies, we need to implement the data forwarding path. So what is the data forwarding path? Actually, in the pipeline, the processor, the result data is generated by ALU or data memory. But this generated result is written back to the register file in the write back stage. So that means even though the pipeline processor already has the result, but if there is no data forwarding path, the following instructions cannot make use of this generated result until the data is written back to the register file. And then, so in order to reduce this wasted cycle, we need a data forwarding path like this one. So in this figure, there are two kinds of data forwarding path. The first data forwarding path is from the output of ALU. That means actually this is, so that is the result of the ALU that propagates the EX and memory stage. So this data is forwarded to the input of ALU, because this data can be used by other alt-time instructions or load instructions or store instructions or any other instructions that make use of the contents of register file. Also, another data forwarding path is from the write back stage. So the final result is the output of this MUX, and then this final result can be the output of the data memory or propagated data from the ALU. So this data can be also forwarded to the input of ALU. Also, this data is written back to the register file like this. We already learned about this path. So there are two kinds of forwarding paths for each input of ALU. Correct? So there are three kinds of data input for this ALU. So we need a multiplexer. So here, and then we need to generate the selection signal for these multiplexers. So the selection signals are generated by forwarding unit. So this forwarding unit detects the forwarding conditions, and if the forwarding conditions are met, so that means the data should be forwarded from the this here or here, then this forwarding unit generate the appropriate selection signals for these multiplexers, like forward A and forward B. And then if these selection signals are determined for data forwarding, then data is selected from the here or here. Okay. And then we already learned what is the forwarding conditions. So intuitively, the data forwarding should be performed in the pipeline processor if RD of RD is the destination register, RD of previous, that means the former instruction is equal to RS1 or RS2 of following instructions. Okay, we already learned using this example, and then let's see the detailed condition. Okay, so and then this slide shows how to represent some data in the pipeline stages. So in the pipeline processor, we learned that this pipeline register is called the name of the stage before this pipeline register, and then the name of stage after this pipeline register. For example, if the pipeline stage before this pipeline register is instruction fetch, then it's an instruction decoding, then this pipeline register is called instruction fetch / instruction decoding pipeline register. All right. So, and then the signals are propagated via this pipeline register. So in order to represent this signal, like this is the RS, for example, here's ID, the EX staging, and it's the ID EX. And if this is the RS1, then we can call this data as the ID / EX dot RS1. So in this example, it's called the register RS1 here. So these signals are represented as this is the pipeline register name and dot and the signal name. Okay. And then if we actually designing pipeline processor is the goal of the last lab assignment. So if you see the some code of this fourth lab assignment, then you can find the similar representation in the system value. So this is the some rule. So it's the ID / EX, that is the pipeline register name, and then dot, and then if we add some signal name after this pipeline register, then that means this signal after the pipeline register, corresponding pipeline register. Okay. So then how can we detect the forwarding conditions? So first, if the so in this figure, as you can see, this folding selection signal is generated if the ALU receives the input from the register file, right? So firstly, we need to check the RS1 and RS2. So if RS1 is valid, is a valid number, then this ALU receives one operand from register file. And then if the RS2 is valid also, then ALU receives a valid operand from register file, right? Okay. Then how can you check the folding condition? So in the previous slide, so I already mentioned that RD of former instruction is equal to the RS1 or RS2 of the following instruction. So you can just write this condition for the folding condition, right? So how can we check the destination register for folding conditions? So in this figure, the data can be folded from the output of EX/memory pipeline register or data from output of memory/write-back pipeline register. Oh, you can say that, oh, this is the output of the multiplexer, not pipeline register, but it's okay. So there is the selection from the output of this part, this result data, and then this result data. So that means that is the output from memory or write back. So, and then you can say that just in this slide. So you can just check the destination register number and source register numbers of it. Okay, so that means this data will be forwarded to the input of the ALU, but you can just check the destination register number. So where is the destination register number for this data? What is the destination register number for this data? 어디죠? Here. So we already learned that the RD is also forwarded to this pipeline stages like this because we need to synchronize the data and the destination register number for write back. So RD is already forwarded through pipeline registers. So the RD, this register for this data is the ex/mem.register RD. Also, the RD for this data is this RD. That is the memory and write back pipeline register that register RD. Are you following me? 이해되나요? 이게 조용하니까 이거 알 수가 없는데. Okay. So, okay. So, if the following instruction, so where is the following instruction? So, in the folding path, the following instruction is in the EX stage, and then the former instructions are in the memory stage or write back stages. Okay, so if the data is forwarded from this memory stage to this data, then we need to check the RD of this instruction, the instruction in memory stage, and RS1 or RS2 of the instruction in EX stage. Got it? So in this example, the sub is here, and the instruction is here. Then the RD of sub is forwarded to this end. Okay. So that is this case. Okay. The forward from EX/mem pipeline register to the input of ALU. And the ALU is in the EX stage. So what is checked? The destination register from EX/mem pipeline register is checked with the RS1 in ID/EX pipeline register. Okay, and then this is the second forward path. So this path to this multiplexer. So for this multiplexer, we need to check the RD and RS2. So that is the forwarding condition from EX/memory pipeline register. And then for the memory/write-back pipeline register, that's easy. So if you understand this condition, then the data forwarding from the write-back stage is also easy. You can just change this pipeline register. Okay. Okay. So that is the data forwarding condition. And then also we need to check if this RD is valid. So if the RD is not valid, we don't need to apply the data forwarding. Okay, when is the RD valid? When is RD valid? If the regular write is 1, so regular write is generated from the control unit, and then you can find the regular write signal in the single cycle processor design. And then if the regular write is 1, that means true, then the RD, the generated result is written back to the register file. So if the regular write is 0, then the data is not written back to the register file. So we can check the validity of this RD, destination register number, with the regular write signal. So this condition is valid only if this regular write is 1. Okay. And then another condition is that the RD is not 0. Why? We already know that x0 is the constant 0. So that means even though the new value is written back to this x0 is always 0. So for example, if we use x0, x1, x2, and then sub x5, x0, x2, for example. So we are the instructions. So in this case, do we need to forward the x0? No. For this case, we must not forward this data, the result of the ALU for this instruction. Why? The x0 should be always 0. But if we forward the result of this add instruction to this following sub instruction, then incorrect value will be given to the ALU. So if RD equal 0, we need to block data forwarding. Okay. Okay. So this is the data forwarding design. And then this is the selection signal. So this box control signal for the data forwarding. Okay. If the port A, this is the selection signal here. If the port A is 00, then the source is from the ID/EX. That means the normal case. The operand is from register file. Okay. And then if the port A is the 10, the data comes from EX/memory pipeline register. And then for the A is a 01, then data comes from the memory/write back register file. Then this is the selection signals for port B. This register, this multiplexer. Okay. And then another special case is the double data hazard. So actually the difficult thing is that actually the base feature or base condition is very simple. So what is the base condition for data forwarding? This is the base condition. The destination RD, the RD is equal to the RS1 or RS2 of the following instruction. But not to generate the correct, in order to implement correct data forwarding logic, then we need to consider the very specific cases like we need to check the validity of the read write. Also, we need to check the number, the destination register number. Okay. We need to exclude the X0. Also, we need to consider this double data hazard case. So double data hazard case is that. So for this hazard, this X1 can be forwarded from the. So let's focus on this instruction. For this instruction, add instruction receives X1. So read X1 from register file here, but this data should be forwarded from the 1, 2, 3. Add 2 or add 1. So when this add instruction is in the EX stage, this add number 2 is in the memory stage, and then this add instruction is the add 1 is in the write back stage, right? So then for this forwarding path, so data can be forwarded from the write back because this X1 is equivalent to this X1. So there can be 2 forwarding paths from the write back to the EX stage, and then another forwarding path is from here to here. It's the memory stage to the EX stage. So that means these 2 forwarding paths are all available, and then it's okay. It's available, and then these 2 forwarding paths meet the forwarding conditions. Right. 그렇죠? 그러니까는 there are 2 different forwarding paths from the so write back to the EX and then memory to EX, and then actually if we consider these forwarding conditions, and then actually forwarding condition also with these 2 forwarding paths both meet the forwarding conditions we learned. Okay, 이게 뭐냐면은 forwarding이 write back에서 EX로 가는 게 있고 여기 있죠. 그 다음에 메모리에서 EX로 가는 거. 이게 다 컨디션이 true. The condition is true. 그러니까는 컨디션 다 만족한다라는 거죠. It meet the conditions. Then how can you select? So do we need to select the forwarding path from the write back to the EX or memory to EX? These two conditions are actually based on what we learned in the previous slide. Oops. These two conditions meet the forwarding conditions. So which one is the correct path? 1, 2. 어떤 거를 선택을 해야 되죠? Which one? It's 2. Why? Because so in the programming code, instructions are executed from top to bottom sequentially. Then what is the latest value for this x1? The latest value is the x1 by add number 2. So this add must receive data from add number 2, right? Because it's the latest value. So we need to activate the forwarding path from memory to EX. Okay, do you understand? So for the double data hazard case, we need to activate this forwarding path. Okay, so that means for this forwarding condition, the data forwarding from memory / write back pipeline register to the EX stage, we need to add the additional condition. This condition that considers the double data hazard cases. Okay. So if the two forwarding paths are all satisfied, then we need to select the forwarding from EX memory to EX. Okay. Okay. For the double data hazard case. Okay. So this is the finalized condition for the port A is equal 0, 1. Okay. So this is the data path with forwarding. So forwarding unit is here. And then this, as you can see, this forwarding unit received its signal. The RD from this pipeline register, and then RD from memory / write back pipeline register. Also, this forwarding unit received control signal. Which control signal? Read, write. Also, this is the read, write for this RD. So the forwarding unit also received control signal from the control unit. So read, write signal from the EX / memory pipeline register. Also another read, write signal from memory slash write back pipeline register. Supporting unit receives these signals and generate selection signals for multiplexers, forwarding multiplexers. Oh, also the supporting unit need to receive RS1 or RS2 signals from this ID slash EX pipeline register. Okay, and generate the control signals for forwarding multiplexer. And that's it. That's the so we complete the forwarding path for the pipeline register. So do you have any questions? So you will be requested to design this forwarding path in the fourth level segment. Okay. Okay, if you have any questions, then let's go to another topic, hazard detection. So in the previous class, we learned that if the formal instruction is load, like load x1, and then the following instruction is requires data from this load instruction, like for example, add x2, x1. So this add received data from this load instruction, right? And then for this case, we cannot make use of forwarding path because the data is generated from data memory, and then when the data is required, the data is not generated yet in the pipeline the processor. Do you remember? Do you remember? So in this case, we need to store pipeline register. So that means store means that the one clock is wasted. So that means that this add instruction need to wait until the data is read from data memory. Okay, and then this process is called the pipeline stores. And then in order to make pipeline stages store, then we need to also implement the control unit that detect this load use data hazard. And then if this hazard is detected, then we need to store the pipelines of this pipeline process. Okay, so the first we need to detect the load use hazard conditions. What is the condition? The condition is the formal instruction is load. And the following instruction requires data read by this load instruction. So this is the load use hazard condition. This is the control signal for load instruction. So memory, if the memory read becomes 1, that means that is the load instruction, right? Right. So the formal instruction. So this is the pipeline register pipeline, like EX stage, ID stage, and memory stage. And then this is the load, and this is add. So we need to check the hazard when the load instruction is in the EX stage and the following instruction is in the ID stage. If not, so if we just detect hazard if the load instruction is memory, and then add instruction is here, then we cannot store the pipeline because this add instruction already is in the EX stage, so it requires data from the load instruction. So for this hazard detection, the hazard is detected when the load instruction is in the EX stage and then the following instruction is in the ID stage. So we check the memory read control signal. So if the memory read is 1, that means it's the load instruction. The data is read from the data memory, and then we just check the RD, the destination register of the load instruction, and RS1, the source register of the following instruction, or RS2 of the following instruction. Okay, so if the hazard is detected, then the load is propagated to the memory stage, and then add the following instruction stays in ID stage. How about the EX stage? Invalid instruction is given generated for EX stage, and then this invalid instruction is called the bubble, or sometimes it's called the loop or nope. So that means the no operation. Sometimes it's called the nope or nope. So no operation. Okay. That's how the data hazard is detected, and then the pipeline is stalled. Okay. So so this is the example of the pipeline stall. So this is the load instruction. The firstly, at the clock count 1, CC1, the load instruction is fetched from the instruction memory. And then at clock count 2, the load instruction is in the ID stage. And then the following instruction, so end instruction, so here is end. And the instruction is fetched from the instruction memory. Okay, and then CC3, the load instruction is in the EX stage, and then at this time is time frame. The end instruction is in the ID stage, and then the following instruction, OR instruction. The OR instruction is in the instruction fetch stage. So I mentioned this load use data hazard is detected when the load instruction is in the EX stage. So in this case, the load is here, EX stage, and then the following instruction, this end instruction, data from the load instruction is in the ID stage. So in this case, the bubble should be generated. Okay. So that means at CC4, the load is propagated to the next stage, but end cannot be propagated to the EX stage. So end needs to stay in the ID stage. So in this case, also the following instruction, OR instruction. OR instruction is in the instruction fetch stage also. This OR instruction need to stay in instruction fetch stage also. Okay. So that means the program counter. So if the bubble is generated, so that means this load use data hazard is detected, and then one bubble is generated. And then in that case, the program counter should be maintained. Are you following me? We good? Do you understand? The program counter is maintained because this OR instruction is also stay in instruction fetch stage. So that means new instruction is not fetched in this case. So that means the program counter value is kept or maintained, kept. Okay? 그렇죠. 버블이 발생하면은 그 인스트럭션이 id 스테이지랑 인스트럭션 fetch 스테이지에 있던 인스트럭션들은 머물러야 되죠. 그러니까는 PC 값이 바뀌면 안 되죠. 그때는 왜냐면 바뀐다는 거는 새로운 인스트럭션이 인스트럭션 메모리에서 다시 읽어 온다는 거니까. So as CC4 load is propagated, and then in the EX stage, the bubble is generated, and is in the instruction fetch, no, ID stage, and OR instruction is the instruction fetch stage. Okay. Then when the load instruction is in the write back stage, the data is read from the data memory, and then this data can be forwarded to the end instruction. Okay, so end instruction can be propagated to the EX stage, then data is forwarded to this ALU, and then as end instruction is propagated to the next stage, the OR instruction is also propagated to the ID stage. So another instruction is fetched from the instruction memory. That's how the bubble is generated by load use hazard, and then the following instructions stayed in its pipeline stages, and then the program counter is maintained. Okay, so that is the hazard detection control. So that means if the hazard is detected, then we need the hazard detection unit. It's called the hazard detection unit. It's called the HDU. So HDU generate the also appropriate control signals for pipelines or program counter or some other control units. Okay. Okay. So let's see how to store the pipeline. So first, if the stall is generated, if the stall means the no operation, no operation. So no operation means that this processor will do nothing for this instruction, nope instruction. Okay, so that means all control signals become 0. Okay, do you understand? So no operation is generated. So the data element of this processor does nothing. So data element unit do nothing for this instruction. So bubble or no loop instruction. So that means all control signals become 0 for this instruction or bubble. So when the bubble is generated, so when the bubble is generated from the ID EX pipeline register, why? And then actually in this example, we already learned that the bubble is generated in the EX stage. So that means this bubble is generated by ID/EX pipeline register. So when the bubble is generated, all control signals from this ID/EX stage become 0. Okay. And then also control signals become zeros. And then how about the instruction fetch and ID stage? So when the pipeline stores the instructions in the ID stage and then instruction fetch stage kept in the its own stage. So what does that means? This pipeline instruction fetch and then ID stage pipeline just keep its values when the bubble is generated. Okay. So this instruction fetch and then ID pipeline stage kept its own value when the bubble is generated because the instruction stays in this ID stage. Okay, do you understand? So I said the pipeline register is just the D flip-flop, so like a D, Q, and then clock signal. So what is the D flip-flop? When the rising edge of the clock, the Q is updated by D, input D. So also we can add the enable signal for this D flip-flop. So that means if the enable signal is 0, then the Q is not updated by this D, even if at the rising edge of the clock signal. So in this case, the Q maintain its own value. So in this case, if the pipeline stores, then instruction fetch and ID stage just enable signal for this pipeline registers becomes 0. So this output of this instruction fetch and then ID stage is maintained. Okay. How about the piece? Piece is not updated. The piece maintains its own value also. So that means the instruction fetch stage, the instruction also stays in the instruction fetch stage. Okay. So that is the maybe data hazard detection unit, and then how the hazard detection unit work in the pipeline processor. Okay, so let's see. So this hazard detection unit received what signal? Memory read signal. Okay, and then also received which signal? RS1 or RS2. Also, it received which signal? Okay. It received this line. Is that this line? HRD. But this RD is the ID/EX dot ID. Okay, and then this hazard detection unit received which signal? Memory read. The memory read is from the ID/EX memory read. Also received RS1 and RS2 from instruction fetch and ID pipeline register. So that is the instruction fetch/ID dot RS1 and RS2. So these signals are required to detect load use hazard cases. Okay, and if this hazard is detected, then the first hazard detection unit to detect hazard by load, and then if the hazard is detected, first generated bubble at EX stage and keep instructions in ID and instruction fetch stage. Okay, so in order to generate the bubble at EX stage, we just make all signals, all control signals 0. So this control signal is generated by hazard detection unit HDU. So that is for is number 1, to generate bubble at EX stage. Also, number 2, keep instructions in ID and IF stage. So this hazard detection unit generate the instruction fetch/ID write signal. So if this signal becomes 0, then this IF/ID pipeline register is not updated. So it keeps its previous value. So the hazard if the hazard is detected, then this if instruction fetch/ID pipeline ID write signal becomes 0. Also, for the instruction fetch stage, we need to control the program counter. For hazard detection unit, also make this PC write signal as 0 if the hazard is detected. Understand? That's it. So the hazard detection unit detect the hazard case, data hazard case by load instruction. So this hazard detection unit receives required signals for detecting data hazard, and then generate control signals for pipeline stores. Then the pipeline stores for making pipeline stored, the first generate bubble at EX stage. That means all control signals to the EX stage become zeros, and then keep instructions in ID and instruction fetch stages. And then for this behavior, with this hazard detection unit, control the instruction fetch/ID write signal and then PC write signal. Okay. 이거 굉장히 이제 중요한데요. So hazard detection is the very important topic in the pipeline processor. It may be difficult to understand, but you need you need to understand how hazard detection unit works. It's, I believe this the question will appear will appear in the final exam about the hazard detection unit, about the hazard detection unit. Okay. Okay. And then also we already learned the so it's not the hardware work, it's the compiler's work. So compiler can adjust the order of the some instructions to avoid this load use hazard. So in this case, we can insert the independent instruction between load and other instruction pair. And then if we adjust some orders, then we can avoid the load use hazard cases. And then we can improve the performance. 뭐 그렇죠. PC 라이트랑 요거는 enable로 들어가는 거고요. dflip lab에 enable로 들어가기 때문에 뭐 normal 케이스 같은 경우에는 얘네들이 다 1일 거고요. 근데 hazard가 디텍션 되면은 걔는 0이 된다. 이렇게 이해를 하면 되겠죠. 컨트롤 시그널이 프로파게이트를 막진 않죠. 이거는 0을 제너레이션 하는 거죠. 컨트롤 시그널은 프로파게이션 되는 걸 막진 않습니다. 그냥 버블을 생성하기 때문에 버블을 생성한다는 건 올 컨트롤 시그널을 0로 만든다는 거고, 여기서는 이제 그러니까는 컨트롤 유닛에서 나오는 그런 시그널 대신 0를 집어넣는 거죠. 그래서 버블이 생성되는 거죠. 됐네? 네, 그렇죠. 모든 컨트롤 시그널이 0이 되면 버블이 됩니다. 왜냐면 뭐 라이트백도 안 할 거고요. 그 다음에 메모리 라이트도 안 할 거고, 뭐 그렇기 때문에 모든 업데이트가 안 일어나죠. 그 인스트럭션에 따라서 뭔가 이제 스테이트 체인지, 제가 그 인스트럭션이 하는 거는 결국에는 그 아키텍처럴 스테이트를 바꾼다라고 했잖아요. 아키텍처럴 스테이트라는 거는 크게 이제 레지스터 파일, 그 다음에 데이터 메모리, 이게 두 개인데 어쨌든 그 두 개를 다 막아버리고 어차피 브랜치라고 디텍션이 돼도 다 막아버리는 거기 때문에 그냥 브랜치도 그냥 0으로 만들고, 그러니까는 얘는 노프 아무것도 안 하는 인스트럭션 되는 거죠. 그 컨트롤 시그널 잘 보면은 우리가 이제 싱글 사이클 프로세서 디자인할 때 어떤 컨트롤 시그널이 이제 생성되는지 배웠잖아요. 그 모든 컨트롤 시그널이 0 되면 어떤 식으로 동작하는지 한번 생각을 해보면 아무것도 안 할 거다라는 것을 알 수 있을 겁니다. 그렇죠. Okay, so I think we need to cover this branch hazard and then exceptions in the next class. And then before going to the next class, I will introduce some very useful tool for this pipeline structure. Okay. So actually, we are learning about the hardware structure or hardware architecture of the processor, and then sometimes it is not easy to understand how the instruction works and then how the instruction is propagated in the pipeline architecture. It is because it's hardware, not software. So actually, the software actually programmer's view for the computer is very simple. So I already explained in the chapter 2. So with in the programmer's view, the computer system is just received a certain instruction, then this instruction generate output by defined ISA. It's a promise between software and hardware, and then that's it. That is the software's view. But the real behavior of hardware is very complex for performance and then some other issues. So it's not easy for software engineers or programmers because programmers' view is very simple. It's very simple, but real hardware's behavior is very complex. So sometimes we need to get help from the simulator. It's called the simulator. So you're not 수요일 수업 없습니다. So in order to understand the behavior of the hardware, then we can get help from the simulator. So what is the simulator? Simulator just emulate. So emulate the behavior of hardware using software. So actually building the real hardware is very difficult, and then it's a costly job. So we can also build we can emulate so just emulate the behavior of the hardware using the software. Okay, because it's not easy to build a real hardware. So it's a software. So for the RISC-V, there are many simulators. So this simulator just emulate the behavior of a RISC-V processor. Also emulate some execution of RISC-V assembly code. So these are some RISC-V assembly simulators like Jupyter or RAS, RVX, RV8. So these simulators can execute the RISC-V codes line by line. So you can visit some these links to see how the simulator works. So this is the example of the RISC-V assembly simulator called the Jupyter. In the Jupyter, as you can see, this assembly simulator can execute the RISC-V assembly codes line by line and then cycle by cycle. And then if the instruction is executed, then this simulator shows the contents of register file or data memory. So as you can see, register here, memory, cache. Okay. And then I will also introduce the graphical architecture simulator. So we are learning about the 5-stage pipeline architecture of RISC-V processor. And I believe some students have struggled to understand how the instruction flows through the RISC-V pipelines, or how the hazard detection unit work, or how the data porting unit work. So this simulator is a graphical architecture simulator. So this simulator shows how instruction flows in the 5-stage pipeline architecture. It's very useful. So I will share. So you can visit this link in the GitHub. Let's see. Here is so can you see this RIPE simulator? So as you can see, this is the 5-stage RISC-V processor. And then this RISC-V stage processor implements the IV32I instructions, not IV64I. And then also, but the structure of this 5-stage pipeline processor is a little bit different from what we are learning in this course, because the textbook just implement the part of instructions, like, but this 5-stage RISC-V processor just implement the all instructions, all IV32I instructions. So this is so also you can select the single cycle processor, and then 5-stage processor, and then 5-stage processor without hazard detection, and then so there are many options. Also, you can select the single cycle processor like this. Also, this structure of the single cycle processor is a little bit different from what we learned in the textbook. It's just you can see you can use this simulator as some reference, not a real hardware implementation of what we learned. Okay, so we select the 5-stage processor here. So you can find, so there are some examples here like assembly code and C code and compiled C code. And then, so you can find the instructions here. So it's called the instruction memory, and the instruction memory includes some assembly instructions here. And you can find the PC here. Okay. And then if you click this arrow, you can see how instructions flow to each stage of this pipeline processor. So instruction propagates to the next stage, and then next stage. Also, you can find that it's a knob, the bubble is generated. So we do not learn about the control hazard yet. So this bubble is generated by control hazard. So it's just a reference. So you can find the contents of the register file here. Okay, but remember that this 5-stage pipeline processor is different from what we are learning in this course, because we just implement the several RISC-V instructions. Okay, so just use this simulator to get help so understand the behavior of a pipeline processor more easily. Okay. It's a very great tool, actually. I believe it's a very great tool. Okay. So I stop here, and we will not have a class. We will not have any class on Wednesday because it's holiday. So please enjoy the holiday, and then let's see in the next week. Okay. Do you have any questions? 네, 수고 많았습니다. 휴일 잘 보내세요.